All right, we are at section 10.6. I'm actually going to cover 10.6 and 10.7, and I'm going to skip parts of 10.6. So 10.6 is calculations of moments of inertia, and 10.7 is rotational kinetic energy, and I'm going to skip the parallel axis theorem. If you understand the parallel axis theorem, the way the author presents it, you can explain it to me, because I think his presentation is a bit confusing. Calculation of moments of inertia. So I is equal to the sum of Ri squared delta Mi. This is a system of discrete particles. If you have a continuous rigid object, then I is equal to the limit as delta Mi approaches 0. As we make each one of those masses smaller, it's the sum I of Ri squared delta Mi. So that's the integral of R squared dm. Now, density, rho, density is equal to the mass divided by the volume, mass per unit volume. And so a small part of dm can be represented as rho dv, the density times a little portion of volume. So I is equal to the integral of density times r squared dv. Now, the density is, that's mass divided by volume, is the volumetric mass density, but we don't always use the volumetric mass density. Notice that that's mass divided by L cubed, mass divided by length cubed in units. That's rho. Now we can use sigma, mass divided by area. Well, that's mass divided by L squared. Well, if you take rho, which is mass over volume, times T of thickness, mass per unit area, you get the T divided by, in other words, L divided by L cubed, it'll leave you L squared in the denominator. So that is mass divided by an area. So that's equal to rho times a thickness. And lambda is equal to mass times a unit length. Well, rho times an area, mass divided by volume times an area, will leave you mass divided by length. So that's mass per unit length. We will have opportunity to use lambda in the upcoming experiment, where we take a ruler and measure the mass of the ruler, especially if it's well, it doesn't matter whether it's a wooden ruler or a metal ruler. You measure the mass of the ruler, and you divide it by 100, you get mass per centimeter, and we'll use that in an upcoming experiment. Okay, parallel axis theorem. I'm gonna skip that. I don't particularly care for the treatment of it in this book. I don't know that it's you're welcome to go through it, but I'm not going to go through it. Now we're going to go. That leads us to 10.7, rotational kinetic energy. The mass of Mi of the rigid object has the same kinetic energy as if it were moving through space with the same speed. So mass I times V, kinetic energy is 1/2 mv squared. So the kinetic energy of the ith portion of this mass is equal to 1/2 mi vi squared. Well, the rotational kinetic energy is equal to the sum of all the kinetic energies is equal to the sum of 1/2 mi vi squared, which is equal to v is related to tangential velocity is related to angular velocity. V is equal to r omega, so we can do that substitution. 1/2 mi vi squared equals 1/2 mi r squared omega squared. Now, why isn't there an omega I squared? Because if it's a solid object, all of the omegas are the same. The angular velocity is the same. The tangential velocity will vary as you go further out. The tangential velocity will increase, and as you go further in towards the origin, the tangential velocity will decrease. But the angular velocity is the same for all particles. If you have a rotating disc, or let's just think of the merry-go-round. Someone riding on the inside of the merry-go-round is traveling at a slower tangential velocity than someone's on the outside of the merry-go-round. All right, so the rotational kinetic energy is 1/2 times the sum of mi/ri squared times omega squared. Well, what is the sum of mi/ri squared? Well, that is the moment of inertia. So the rotational kinetic energy is equal to 1/2 I omega squared. So the translational kinetic energy up on top is 1/2 m mass times velocity squared. The rotational kinetic energy is 1/2 I, the moment of inertia, times omega squared. Okay, now a section of hollow pipe and a solid cylinder have the same radius, mass, and length. They both rotate about their long central axis with the same angular speed. Which object has the higher rotational kinetic energy? Well, let's go back here. The rotational kinetic energy is equal to 1/2 I omega squared. Well, if they both have the same rotational, the same angular velocity, all it depends on is I. So which one has the greater I? Well, let's look. Let's stop this particular share and go to the iPad where I have the picture from the textbook. Oh, I haven't, sorry about that. I haven't completed. Why isn't it? Well, I can't, I've got it plugged in. I don't know why it's not, let's see, stop share, share. Let's try that again. And it's not showing it. Okay, well, let's go backwards. Let's, do we have the right, okay, we're wasting too much time with this. Let's just go back to the moments of inertia, and there it is. There's the you can think of this problem. It's a hollow shell, and one's a solid rod. So let's look at this upper left-hand corner. The hoop has a I of mr squared, and the solid cylinder has a I of 1/2 mr squared. So it has half the moment of inertia as the shell. So if we go back down here, we'll see that the let's get back to the problem. The hollow pipe and solid cylinder have the same radius, mass. They both rotate about their long central axis with the same angular speed. Which object has the higher rotational kinetic energy? The hollow pipe has twice the moment of inertia as the solid cylinder does, so it'll be A, the hollow pipe. And that ends our discussion for that section. So we'll stop